Hi students, the topics for today's class is atomic spectra, spectral series and Bohr's model of an atom. Atomic spectra. When an atomic gas or vapor at low pressure is excited by passing an electric current, the emitted radiation has spectrums which consist of certain specific wavelengths only. A spectrum of this type is called line emission spectrum. Line emission spectrum consists of bright lines against a dark background. The study of this spectra serves as a fingerprint for identification of the gas. When white light is passed through a gas, the transmitted light was analyzed using a spectrometer. It consists of dark lines against a bright background. These dark lines correspond to those wavelengths which were found in emission line spectrum. This is called an absorption spectrum. Line emission spectrum is observed when an electron in the higher energy level gets de-excited to a lower energy level by emitting a photon. Absorption spectrum is observed when an electron in lower energy level absorbs energy from a photon and gets excited to a higher energy level. Consider an hydrogen atom which has the simplest spectrum. In the spectrum, there was no order or regularity in the spectral lines. But the spacing between lines within certain sets of hydrogen spectrum was found to be decreasing. Each of these sets of lines is called a spectral series. Swedish school teacher Johann Jacob Balmer was the first to observe such series in the visible region of the hydrogen spectrum and called the spectral series as Balmer series. The line with largest wavelength 656.3 nanometer in red is called H alpha line. The next line with wavelength 486.1 nanometer in the blue-green is called H beta line. The third line with wavelength 434.1 nanometer in the violet is called H gamma line, and so on. As wavelength decreases, the lines appear closer together and were found weaker in intensity. Balmer found a simple empirical formula for the observed wavelengths as 1 by lambda equal to r times 1 by 2 square minus 1 by n square, where lambda is the wavelength, r is the Rydberg constant, and n equal to 3, 4, 5, and so on. The value for r is 1.097 into 10 power 7 per meter. This equation is also called Balmer formula. Substituting n equal to 3 in Balmer formula, we get the wavelength of H alpha line. For n equal to 4, we get the wavelength of H beta line, and so on. For n equal to infinity, we get the shortest wavelength in the Balmer series as 364.6 nanometer. Beyond this limit, there are no distinct lines, but instead we observe a faint continuous spectrum. Other series of spectra for hydrogen were discovered and named after the discoverers as Lyman series. for which the final state corresponds to n equal to 1 and their initial states corresponds to n equal to 2, 3, 4, 5, etc. The equation to calculate the wavelength of Lyman series is 1 by lambda equal to RH of 1 by 1 square minus 1 by Ni square. Similarly, for Paschen series, the final state corresponds to n equal to 3 and their initial states of an electron corresponds to 4, 5, 6 and so on. Bracket series n equal to 4, Ni corresponds to 5, 6, 7 and so on. For fun series, final state is 5 and Ni initial states to be 6, 7, 8 and so on. To calculate the shortest wavelength in any of the above series, we can substitute Ni as infinity. The Lyman series lies in the ultraviolet region of the spectrum, whereas Paschen and Bracket in infrared and Fun series lies in far infrared region. The above equation can also be written in terms of frequency as mu is equal to R into C of 1 by 2 square minus 1 by n square. And the equations written above are applicable only for few elements. However, these results are empirical and do not give any reason as why only certain frequencies are observed in the hydrogen spectrum. In Rutherford's atom model, a revolving electron is experiencing a centripetal force. According to classical electromagnetic theory, the electron must radiate energy in the form of electromagnetic waves. As the electron loses energy continuously, it must spiral inwards and eventually fall into the nucleus. Therefore, such an atom cannot be stable. The frequency of electromagnetic waves emitted by the revolving electrons is equal to frequency of revolution. Hence, they would emit continuous spectrum. But we observe that the atoms emit only line spectrum. Thus, Rutherford's atom model fails to explain the stability of an atom and the line spectra emitted by the atoms. The failure of Rutherford's atom model was later modified by Niels Bohr by adding the ideas of newly developing quantum hypothesis. Bohr's postulates. Postulate 1. An electron in an atom revolves around the nucleus in certain permitted orbits called stationary orbits without the emission of energy. Each state in which an atom revolves has definite total energy. Postulate 2. An electron can revolve around the nucleus only if an electron satisfies the condition of L equal to nh by 2 pi, where L is the angular momentum. Postulate 3. An atom can radiate energy only when an electron undergoes transition from a higher energy level to a lower energy level. The energy of a photon h mu will be equal to the difference of energies of initial and the final states. Considering Bohr's postulate, let us try and derive an expression for radius of an electron in nth orbit of the hydrogen atom. Consider an electron of mass m, charge e, revolving round the nucleus of radius r with a velocity v. The electrostatic force of attraction between the electron and the nucleus provides the necessary centripetal force. That is Fe equal to Fc. Substituting for Fe and Fc, we get 1 by 4 pi epsilon naught Ze square by r square is equal to mv square by r. mv square r is equal to Ze square by 4 pi epsilon naught. We shall call this as equation 1. We know that from Bohr's postulate, angular momentum is integral multiple of h by 2 pi. Substituting for angular momentum as mvr, we get equation as mvr equal to nh by 2 pi. Squaring equation 2, we get m square v square r square equal to n square h square by 4 pi square. Calling this as equation 3. Now dividing equation 3 by equation 1, we get mr equal to n square h square epsilon by pi z e square. Therefore, Rn is equal to n square h square epsilon naught by pi m z square. Substituting for z equal to 1, we get the radius of nth stationary orbit is n square h square epsilon naught by pi m e square. The first orbit of hydrogen atom is called Bohr orbit and its radius is called Bohr's radius. Bohr's radius A0 is equal to h square epsilon naught by pi m e square, which is equal to 5.29 into 10 power minus 10 meter. The radius Rn in any nth state increases as n increases. Similarly, let us obtain the equation for velocity of the electron in nth orbit of hydrogen atom. Consider an electron of mass m, charge e, revolving around the nucleus in a circular orbit of radius r with a velocity v. The electrostatic force of attraction between the electron and the nucleus provides the necessary centripetal force. Substituting for Fe and Fc, we get mv square r is equal to Ze square by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. From Bohr's postulate, we can write mvr is equal to nh by 2 pi. Dividing equation 1 by 2, we get Vn is equal to Ze square by 2 epsilon nh. In this equation, except n, all the other parameters are found to be a constant. The velocity of electron in Bohr radius is found to be equal to 2.18 into 10 power 6 meter per second. It is found that as n increases, the velocity of electron decreases. The next derivation is the total energy of the electron in nth orbit of hydrogen atom. Let us consider an electron of certain mass m charge E revolving round the nucleus of radius r. The revolving electron has potential energy because it is in the electrostatic field of the nucleus and kinetic energy by virtue of its motion. Therefore, total energy E is equal to sum of potential energy and kinetic energy. Potential energy U is equal to minus E square by 4 pi epsilon naught R, where epsilon naught is the permittivity of free space. Kinetic energy is half mv square. We know that electrostatic force of attraction Fe is equal to centripetal force Fc. Substituting for Fe and Fc, we get mv square is equal to Ze square by 4 pi epsilon naught r. Substituting mv square in kinetic energy equation, we get K as half of Ze square by 4 pi epsilon naught r. Kinetic energy is equal to Ze square by 8 pi epsilon naught r. Substituting potential energy and kinetic energy, we get total energy E is equal to minus Ze square by 8 pi epsilon naught r. We know that radius of an electron in nth orbit is n square h square epsilon naught by pi m Ze square. Therefore, on substituting Rn in equation of total energy, we get En is equal to minus me power 4 h epsilon square n square h square. Substituting the value of constants in the equation of total energy, we get En equal to minus 2.18 into 10 power minus 18 by n square in joules. Total energy can also be expressed in terms of electron volt as minus 13.6 by n square. The negative sign in the equation tells us that electron is bound to the nucleus and energy must be supplied to remove an electron from the field of the nucleus.